then if no one else has homework questions, then I'll get the screen share going on this end and we can dive back in. So I am on slide 53. Let me see if I can move this thing out of the way. Yes, I know participants can see my screen. That was the point. I'm already getting the dreaded low system resources message. Can you still see me and hear me? Or am I frozen yet? We're good so far? Okay. Please do let me know if I get frozen, because then I can stop talking, wait for it to catch up, and repeat myself as needed, and potentially kill my camera if it comes to that, so that I can have some processing resources. My little laptop is working very hard to try and do all this at once. So, anywho, welcome back, folks. Thanks for joining us. I appreciate everyone joining us here. I know that you have a choice as to whether or not you attend class, and I thank you for spending your time here. It makes it a lot more fun for me, especially. I am going to finish up then the last part of lecture 2 here, talking about effect size, sample size, test statistics, and eventually heading into decision errors and power. So the idea of effect size is something we talked about last time. Do you remember that as a terminology? Effect size? What-ish? I like the honesty. Maybe I remember that. I'm not sure. What is effect size as a general definition? Any ideas? We talked about 2 measures of effect size, if that may help. We have a R correlation metric, as well as a what's known as a Cohen's d, or standardized mean difference metric. Why would those be useful to provide? We got a comment, the more people in the sample, the greater the chances there are to identify differences. That is true. That is true. So are you saying then that your significance test is potentially, I want to say biased, but it is a function of sample size? That is true. The effect size is independent of the number of people. Yes. So it's trying to describe in a metric that is readily understandable just how strong a relationship is that is being captured by your slope. So in our example, we had a slope of 1.82, which in order to know what that means, you have to know what the units of x are and what the units of y are. So that number itself is not informative on its own. So we want to try and express a slope in a way that is in a standardized metric where everybody knows what the range could be, and thus how big the relationship actually is. Effect size shows the magnitude of the significance. Yeah, I'll go with that. It's like it's additional information beyond just significant or not, because that distinction is a function of whether or not what we've found is expected or unexpected. And just because it would happen less than alpha, less than 5% of the time, that puts it into unexpected, puts it into reject the null hypothesis, puts it into significant. We don't have a sense of how big the relationship is just because it's significant. So effect size helps to convey just how large the effect is, not just whether it's significant. And it is independent of sample size.
Hi, Mom.
It is the case that if you have a small sample, the effect that you get back is going to be noisier, is going to be more inconsistent, but the number that it is irrespective of sample size. So should we back up a few slides and talk about effect size? Would that be helpful? Maybe?
Yes, please.
Yeah, let's do that. So here's one. This is Cohen's d. So that is a standardized mean difference. So the units of d are in standard deviation units. So for example, in last week we looked at the difference in predicted income between people who are married versus not married, and we can express how large that difference is in D units, how many standard deviations apart are the two group means. That's one way to do it. The other one is R down here. Let me back up a couple more slides. It backs up slowly because my computer's working very hard. Come on, you can do it. A few more, almost. There we go. This is the one I wanted. The other metric that effect sizes are commonly reported in is correlation metric R. So for instance, Pearson correlation ranges between -1 to 1, where the direction of the relationship is conveyed by the sign. So a negative correlation goes with a negative slope, means as y goes up, or as x goes up, y goes down. That's what a negative would mean. A positive would mean as x goes up, y goes up also. So the sign covers the direction of the relationship. The magnitude of the correlation describes the size of the relationship. So 1 is perfect, either -1 or +1, and 0 means no relationship. So we can take our unstandardized slope, so in units of x and in units of y, basically strip off the units and we can convert that slope into a correlation. And there are really two reasons to do that. One is to convey the size of the effect, but the other is to use it for planning purposes in terms of how many subjects do you actually need to collect data from to have a decent shot at finding an effect of that magnitude. So that's the part that we haven't really talked about yet. Okay, does that help remind a little bit? So the idea of effect size, it's an additional piece of information you owe your reader as to what happened in your model. Not just whether or not you have a significant relationship, because you can have a significant relationship if you have a lot of people. It's how big the relationship is in a more readily conveyed metric. So R is a metric that people know what to do with. They know that a positive correlation of 1 is a perfect relationship. That's the highest it can be. And somewhere between 0 and 1 is an imperfect but positive relationship, for instance. Okay, now trying to go forward in the slides very slowly. Come on, you can do it. Come on. I feel like I'm talking to a pet. My pet laptop. Come on. There we go. This is the one I wanted. So this slide is trying to put all of these ideas kind of into the same space. So we have a relationship potentially that we're interested in testing. So we put in a predictor variable into a model predicting an outcome in order to answer the question, are these two things related? If x goes up, what is predicted to happen to y? Is it predicted to go up too? Is it predicted to not change at all, meaning there's no relationship, or is it predicted to go down? So the null hypothesis, what we expect to find, sort of the benchmark against which we're going to judge what happened, is that there's no effect. So that translates into a slope of 0, or an R of 0, or a D of 0, basically that there's no relationship. And as you move along this line here, this is meant to convey effect size. So the further you move to the right, the stronger you have of an effect. So like a correlation of 1 would be at the end of the line here. The relationship between whether or not a given effect is significant is determined by your sample size. So there's an arbitrary line in the sand, that this blue line right here, where if you have enough people, then that effect size would be declared significant, and if you don't have enough people, that effect size would be declared not significant. So test statistics that we use to assess whether or not we have a significant slope are a function of effect size and sample size. So they're conflating two different things, which is why we want to report effect size and not just significance. So a given slope is more likely to be significant. What that means is that The relationship is sufficiently unexpected if the true relationship were 0. That's what significant means. It's tied to your p-value, which is the probability of observing that relationship if the null hypothesis is true. The more people you have, the easier it is to declare something unexpected. The boundaries move in. It's an easier hurdle to get over if you have more people. Likewise, the stronger your effect, the easier it is to declare it significant. But we want to be able to quantify just how large the effect is, independent of whether or not it's significant, because of the tie with sample size with respect to significance testing. So the blue line here that divides non-significant from significant moves to the right, meaning it's harder to say that a given effect is significant if you have a lower alpha level, so if you're being more conservative with what you call unexpected, or if you have fewer people. And so the term that people often describe sample size considerations with is statistical power. So that's where we're headed next. So decision errors. If I'm testing a relationship between a predictor X and an outcome Y, then I can get that correct with respect to what it truly is in the population 2 different ways, and I can screw it up 2 different ways. So let's say that I have a null hypothesis that there is no relationship between these 2 variables. So that translates into a null hypothesis HO for the slope of 0. And let's say that I'm doing a 2-tailed alternative, meaning that I'm willing to say that the slope could be unexpectedly positive or it's unexpectedly negative. I'm allowing for both of those possibilities, and 5% of the total room is allocated across the 2, so 2.5 in each side. So then if in reality the null hypothesis is correct, and I make the decision to retain it, meaning I say something is not significant, then I can get that correct in this cell. If in reality the null hypothesis is wrong, and I say that I'm rejecting it, I can get it correct down here. But we're focusing on the 2 ways to get it wrong that are in these off cells here in the red and the yellow. So one way to get it wrong is to have a false alarm. I thought there is a relationship, but in reality, in the population, the thing that I don't have access to, there is no relationship. So I jumped the gun, I said I have a relationship, I don't actually have one. That type of decision error of a false positive, false alarm, is called a type 1 error. And these are terms that are universally accepted, by the way, in describing this type of phenomenon. It's type 1, and it's always written with like the I for 1 instead of the number 1. I don't know who decided that, but that's the way it's always written. So we know from the get-go what the likelihood is of a type 1 error, a false positive, because that is your alpha rate. You set that. So alpha is the proportion of time you would expect to find a result that extreme if the null hypothesis were true. And so if we pick alpha of 0.05, then 5% of the time we're going to have a false positive. That's what it means. If we want to be conservative, if we don't want to have false positives, then should we take alpha and increase it or decrease it if we want to be conservative? Yeah, decrease it. Yeah, trying to ask questions people can answer with their thumbs. So yeah, if we want to be conservative, we decrease alpha. We change it from maybe 0.05 to 0.01. So then we're saying that it's a harder boundary to cross to get to where unexpected starts, and we would only have a false alarm 1% of the time. If we wanted to be more lenient, we would increase alpha instead, maybe 10% of the time. The other way to get this wrong is what's known as a type 2 error, and that is a miss. There is a relationship in the population, but you missed it. You said that the slope was not significant. You should have said it was significant. That type of miss. That's what's known as a type 2 error. And it's usually expressed as the opposite idea, which is power. So 1 minus type 2 error is power. And power is the probability of finding an effect that's really there. So that's the part where sample size comes in, is how many people do we need to have a good chance of finding something if it's really there? How many people do we need to have adequate power, as it's called? So type 2 error is something you have to worry about if you retain the null hypothesis, if you say there's no relationship or the relationship is non-significant. So there's only, each of these is in a different sort of point of reference with respect to what the truth is. A type 1 error is possible if in reality there's no relationship but you think you found one. A type 2 error is only possible if there is a relationship in reality, but you didn't find it. And unlike alpha of 0.05, the conventional acceptable level of type 2 error rate, does anyone have a guess? It's not 0.05 for type 2 error like it is for type 1. Do you know what it is? Anyone? We haven't talked about this yet. I'm just curious if this has come up in other contexts for you. It's actually 0.2. The conventional level of acceptable type 2 error rate is 0.2 because that translates into power of 0.8. So type 2 errors are more permissible under traditional standards than type 1 errors. For better or worse, that's the way that its convention is set up. Yeah, 100 minus 0.05, so it'd be 95% of the time you don't make a type 1 error in that case. The type 2 error is from a different reference distribution. And by the way, this was the concept that on my test, when I was taking stats, I wrote, I'm sorry, I still don't understand this. And I got 1 point out of 4 for admitting I didn't understand it, because this is confusing. The hard part is that you're talking about like two different ideas of reality, like as your baseline. What happens if there really is no effect to be found is one situation, that's type 1 error or not. And then if there really is an effect to be found is the other, and that's type 2 error versus power. So I got pictures. This is the type of picture that is typically shown to try and illustrate this concept of type 1 versus type 2 error and power. And I find it hella confusing. I'll just put that out there. I borrowed the picture and I added the all of the boxes pointing to things, and I still find it confusing, and I made the damn graphic. So I'm going to skip this, because if this helps you, great. If not, I got something that's going to work a little better, hopefully. So let's say I'm going back to my fake person generator from this. Question, is the 0.02 from Bonferroni's correction? Bonferroni is when you divide your alpha by the number of tests that you want to do. So the critical, like what it takes to be significant, is more conservative. So like if I were going to do 3 tests and I wanted to keep the total combined type 1 error rate at 0.05, the alpha I would use for each test would be 0.05 divided by 3. So that's one approach that people use to be more stringent, is known as a Bonferroni correction. So, okay, back to power. So let's say that I'm playing God here. I'm creating fake people where I know the truth. That way I can use this as a demonstration. We never know what the population is unless you make up data, but I'm going to make up data. So I simulated 100,000 fake people for 2 variables in which the true relationship between the 2 variables corresponds to a correlation of 0.3 as my effect size. So that number, then, the fact that it's positive, that tells me that as x goes up, y is predicted to go up. As x goes up by 1 standard deviation, y is predicted to go up by 0.3 standard deviations. So it's, I'd say, medium-ish with respect to effect size. So I know that that is the truth. Okay, now my question is, in a given sample, what are the odds I'm going to actually find that 0.3 to be significant? And what are the odds I'm going to miss? So we're looking at type 2 error, because this is a situation in which in reality there is a relationship between two variables to be found, and that relationship to be found is 0.3. So I drew 1,000 samples each of sample size 42, 63, or 85 people. Now I know those seem very arbitrary, but there is a reason, I promise, that I picked that one. So in my data set of 100,000 people, I grab a sample of 42, I estimate the slope, get the correlation for it. I grab another sample of 42, estimate the slope, get the correlation for it, and so forth. And I do that 1,000 times for 42 people, 1,000 times of 63 people, 1,000 times of 85 people. Okay, with me so far? So these histograms then, these are sampling distributions for that correlation, meaning each point is what the R actually turned out to be in that sample of 42 or 63 or 85. So this is showing the inconsistency in the results that I get back when I only have 42 people relative to what I should have found. So if I only have 42 people, on average it gets it right. So the lines in here, this is at a correlation of 0.3. But I'm not going to get a 0.3 every time. The obtained correlation that I got from 42 people ranged from, looks like there's down under negative 0.3, so a relationship of the same size in the opposite direction, all the way up past 0.6. So in any one sample, what I get back is not going to be right. The question is, how variable is it? As I get more people in each sample, the resulting correlation I get back from any one sample becomes more consistent, less variable. These distributions are collapsing towards a center that is more well defined. So by the time I get to 85 people, I'm getting the right answer on average, but I have a lot less variability around it. Most of the correlations I find with 85 people are somewhere between 0 and 0.6, so it's not as variable. So all things being equal, you can get a more consistent estimate of effect size the more people you have. But the correlation of 0.3 holds regardless of sample size. Okay, does that distinction make sense? Effect size has nothing to do with how many people you have. But how likely you are to get the right effect size does have to do with how many people you have. You will get way more variability in the relationship you obtain if you have fewer people than if you have more people. And trying to anticipate then how variable that relationship is going to be is the basis of doing what's known as a power analysis. So I've got a second picture here. I have divided up each of these same histograms. So this is now the x-axis is my t-test statistic that goes with my slope. So t is estimate over standard error. T tells me how many standard errors away from the null hypothesis my slope estimate is. So I've got two lines on each of these here. I've got a t of just past 2 as where significance starts. So at this sample size, the critical value for where unexpected 0.05 begins is just past 2. And then it's a little bit closer to 2 for 63, and then a little bit closer to 2 yet for 85. So 2-ish, but it moves a little bit as a function of your sample size. And then I also put a boundary on the same t-test statistic in the opposite side. So anything to the right of a t of 2 is a correlation that would be called significant, meaning that if the null hypothesis of 0 were true, I would obtain a correlation that big less than 5% of the time, so I'm going to call that significant. And anything to the left of that t of 2 is not significant. So the left-hand area here is a not significant correlation. The right-hand area is a significant correlation. So even though I know in reality the population correlation is 0.3, I'm not always going to find that 0.3 in the sample, and I'm not always going to find it to be significant. So I can literally compute the proportion of samples in which I ended up on the left side and the proportion of samples in which I ended up on the right side. Right side is power. Left side is type 1 error. And I'm looking at this table going, yeah, I totally should have reversed these two columns. My bad. But I have it color coded. Does that count for something? So the proportion of samples in which my correlation was found to be significant is my power. And at 42 people, it's half the time. So think about that for a second. I know that I should have a correlation of 0.3. Only half the time did I decide that I had a correlation that was greater than 0. Because of sampling variability, inconsistency in what the correlation became. So half the time I got it wrong. With 42 people, half the time I said, nope, nothing to see here, folks. But actually there was a correlation of 0.3. I do a better job at 63 people. I get it right 66% of the time and wrong 37% of the time. And by the time I get to 85 people, I'm at just about the 80% mark that I'm supposed to be aiming for. So this last row is what we are told in the social sciences we should strive for. A type 1 error rate, a whoops, I missed it, should have called it significant, but I didn't, of 20%. And a yep, I found it, it's there, with 80%. So we are told to aim for 80%, I will find it if it's there, 20%, I will not find it if it's there. Okay, question. The red significance bars, are they at 5% alpha or 20% like beta? The red significance bars are at alpha. So a cutoff T of 2-ish corresponds to a 5% rejection region for where unexpected is. Does that help? So the 5% is what delineates where the dividing line is here. Sample size and 5% tells me where the dividing line is for significance. But the frequency of being on either side is type 2 error versus power. Yep. Okay. Other questions or things I can repeat or say again or say differently? Cheers. Now, do you want to know why I picked 42, 63, and 85? I know it's a rhetorical question, but I'm going to ask it anyway. Do you want to know why? I had a reason. I promise. Because somebody already figured this out. So the idea of doing sample size planning. People come to me, I'm planning my dissertation, I need to figure out how many subjects I need. I'll stop you right there. The answer is more. The answer is always more. But more is not an acceptable answer. You got to come up with something. So here is the logic by which you can come up with something. There are power tables that have been derived from these sorts of simulation experiments and probably some calculus and stuff like that under the hood, such as this one. So this is a classic book, Cohen's Power Analysis book. So how we read these tables is the effect size that you believe to be there in truth. So in the population, effect size is across the columns here. So this is an R table that starts at an R of 0.1. So like a really small relationship, and it ends at an R of 0.9, which is like almost perfect, huge relationship. And R in these tables is positive because the exact same numbers would hold if the R were negative instead. Because a negative relationship is just as strong, it's just in the opposite direction. So positive R means as X goes up, Y is predicted to go up. A negative R would mean as X goes up, Y is predicted to go down, but it's still the same size. So we only need to worry about one direction.
Can you repeat that one more time, please? As like as X goes up, Y goes down.
Yep.
And as
So a positive slope, a positive correlation, corresponds to as X goes up, Y is predicted to go up also. A negative slope, which corresponds to a negative correlation, means as X goes up, Y is predicted to go down instead.
Thank you.
My pleasure. So the sign tells you the direction of the relationship, the number tells you the magnitude. So an R of 0.8 is just as strong as an R of negative 0.8. So across the top is effect size. The rows then are power. The proportion of samples in which an effect of that size would be deemed significant using an alpha of 0.05 in this table. So there's different tables for different alphas. So I've highlighted the row where power is 0.8. So if I think that I am going to be able to find a correlation of 0.3, and I want to do so where 80% of the time I would get that correlation to be significant, then I need at least 85 people. So the numbers inside the table is the sample size needed to detect that effect size across the top with that probability. So on the previous slide here, I had 85 people, and in a sample size of 85, 79% of the time I got a significant result, and 21% of the time I didn't. Damn if it doesn't map on exactly. It works. So I need 85 people to be able to have an 80% probability of detecting an R of 0.3 to be significant using an alpha of 0.05. That means if I redo the same study over and over and over again, 80% of the time I will call an R of 0.3 significant, and 20% of the time I will call it non-significant. And the reason that I call the same number different things is because I'm not getting the same number back. So at 85, the correlation I get in any one sample is somewhere between 0 and 0.6. So that inconsistency across samples is what drives my inconsistency in concluding that it's significant or not. Well, what if I don't have enough money to pay 85 subjects? Can I have maybe 60 instead? Well, you can, but now your power is 2/3. So only 66% of the time will you declare a correlation of 0.3 to be significant if you have a sample size of 63. And what if I only have money for 42 people? Half and half. So this process of I start with an effect size that I expect, and then I look for the row of 0.8 and figure out how many people I need is called power analysis. So look at the difference in these numbers. If I have an R of 0.9, a tremendously huge relationship, I need 6 people to find it. I have 80% probability of finding an R of 0.9 even if I only have 6 people. If I want to be absolutely certain I'm not going to miss it, the last row here, power of almost 1, 11 people. But now look what happens as you move to the left here. The smaller the effect size is in the population, the more people you need to find it, and it gets exponentially harder the closer you get to 0. So if I want to have a guarantee, basically, to find an R of 0.1 to be significant, I need 1,828 people. Okay, questions on the table or the concepts?
I have a question. I don't know how to word it.
Okay.
So so the lower the R, the more significant to the population that we're testing is.
The lower the R, the more people you need to find it reliably.
Meaning, and that means the effect size. This is the effect size, right?
The lower the R is the lower the effect size, yes.
Okay. Thank you.
Yes.
The lower the R, the lower effect.
Yeah, the lower the R, the lower the effect size, the smaller the relationship. The less it matters that you have X in predicting Y. So the smaller the effect, the more people you need to be able to detect it reliably. And what that is referring to reliably is trying to anticipate what the sampling variation would be. I know that the right answer is 0.3. I don't get 0.3 back every single time. There's noise. So how much noise are you willing to tolerate? So this is traditionally referred to as power analysis. And these sorts of tables are used for either very simple models or very simple problems. To be able to do this for more complex models, there are programs you can use. So there's a program called GPower that's a standalone thing that people use for sample size calculations. There's various R packages. When I do this for people's grant applications, I actually do it via simulation. So I literally make up data that have the characteristics we hope to find, and then I see how many people we need to be able to detect it with 80% power. So what I just did, essentially, is what I do. Now, the way that this happens in reality, though, is not this. The way this happens in reality is backwards. What happens in reality is someone comes to my office, or asks to meet me on Zoom, I should say, and says, yeah, I can afford 50 people. What can you do with that? Because either because of money or time, or literally there's no more than 50 people that you can, like, that exist. You're stuck with 50. What can I get with that? That's a reasonable question. So that idea then reframes this exercise from a different perspective into something that's called a sensitivity analysis, where what you're looking to do is find what is the minimum detectable effect size. So if I have 30 people, I find 30 in this table here, right around here. If I only have 30 people, here's 28 in the cell, that's close enough, then I can detect an R of 0.5 or greater. That's the minimum effect size that I have at least 80% power to detect if I only have 28 people. What if I have 50 people? Well, somewhere just past 0.4 here. So for 50 people, I have 80% power to detect an R of 0.4 instead. So then it becomes a question of, is that reasonable? Is an R of 0.4, is that likely to be found given the context of what you're doing in your research? What have other people found? Have they found anything that big? Because a legit criticism of your potential study is, yeah, you only have power to detect like something perfect, but you're not going to find something that strong. So what's the point of doing it? So a lot of times people will do pilot studies with very few people to try and get a sense of what the effect size is, and then they'll try to figure out how many people they need to reasonably detect that effect size. So you can take published work that you've read about in this area and try to reverse engineer an effect size if they don't give one to you out of their t-test statistics. The formulas that I had a couple slides ago allow you to convert T into D or T into R or R into D. You can, and so there's actually a course right now that's being offered on meta-analysis that covers some of this idea. So how do you take publish literature, get effect sizes out of it so that you can do study planning kinds of things. Okay. All right. So, questions? So to try and recap then, what you do and do not need to worry about with respect to these sorts of decisions. So given alpha, which you define a priori before you do the analysis and theory, before you even collect the data, as to what type 1 error rate you're willing to live with for percent unexpected, then your test result, so estimate minus your null hypothesis divided by standard error gives you t. T tells you how many standard errors your slope is away from the null hypothesis. If t is outside the critical region, so basically greater than 2 or smaller than -2, then you will have a p-value that's less than alpha. So you would say the result is sufficiently unexpected. You reject the null hypothesis, you call it significant. So if you would find a slope that big less than 5% of the time, if the null hypothesis were true, you call it significant, reject HO. Seems unlikely that you'd find a slope that big. Null hypothesis, probably not correct. If that's your situation, you're saying, yes, I found a relationship and it's significant. It's sufficiently unexpected. You do have to worry about making a false alarm, a type 1 error. And you know from the get-go what your type 1 error rate is because that's your p-value. So if you have a p-value of 0.02, that tells you 2% of the time you'd find a relationship this big even if the null hypothesis of no relationship were true. If you're willing to live with that, that's your type 1 error rate. You don't have to worry about type 2 error because you're not over in that situation. You couldn't have missed anything because you didn't miss. You said, I found it. However, a result that has low power is less likely to replicate. So if we go back to my table here, and let's say that I only have 20 people, but I have a correlation of 0.3 and I found it significant. I got lucky. Because I only have 25% power. That means if I redid my study, I'd only have come to the same conclusion that I have a significant correlation 25% of the time. So this is a big deal in science right now, the replication crisis and all of that, right? These sorts of effects where you find something, p's less than 0.05, but you got lucky. Those are the things that people worry about. And so it sounds unnecessary to worry about power for an effect that's significant because by definition you had enough power if you found it. The question is, would you find it again? So things that are significant but you don't have a lot of power are less likely to replicate. You could have just gotten lucky. Come on, there we go. Now the other half of this here. If your slope is inside the expected region, so within a t of 2-ish, then you say, nah, sorry, I have a relationship, but it's not significant. It is sufficiently expected just from inconsistency if the null hypothesis is true. So I do not reject the null hypothesis or I retain it, whichever you want to say. Can't say except, but you can say the other ones. Then I would say my slope is non-significant. So you don't have to worry about a false alarm or a type 1 error because you didn't say you found anything. But you do have to worry about a miss. So then if you say, nope, didn't find it, sorry, reviewer 3 can come back and say, well, you didn't find it because you didn't have enough power. And the only way to answer that potential criticism is to say, no, I didn't find it because it wasn't worth finding. You say, I didn't find it because the effect size was tiny and I would have needed 1 million people to have decent power to detect the tiny effect size. So you have to worry about justifying your power whenever you don't find something, whenever you have a type 2 error as possible. So power and type 2 error are inversely related. 80% power means 20% type 2 error. And that's the conventional level that we're told to aim for. All right, 248. How we doing? Questions? So if you come to me and say, how many people do I need in my dissertation? We're going to get the table out. And my question would be, do you have a fixed sample size that you have to work with? In which case we figure out what your minimum detectable effect size is, or do you want to try and anticipate what the trade-offs are of adding more people? And for anything more complicated than just a bivariate analysis, this table may not be sufficient, but it's a good place to get started. They also have these tables for D, by the way. I have a handout, I think that's on the webpage somewhere, that has R tables and D tables at alpha 0.01 and 0.05 that I use for these things. So, all right. I think then, did we finish it? Yes! We're actually finishing lecture 2! Hooray! So, wrapping up, what did we learn in this unit here? So we're working with linear models, and the term linear means that it's slope times variable plus slope times variable. Oh, am I frozen? No? We're okay? All right. So slope times variable plus slope times variable, that's what linear means. The term general in general linear model means that we are predicting outcomes that are supposed to be continuous and whose e's, residuals, are supposed to be normal. We can do the same sorts of modeling for other kinds of outcomes too. That's my other class. So the class I teach before this is called Generalized Linear Models, where we're learning how this process has to adapt in order to predict, say, a binary outcome or an ordinal outcome or any kind of outcome that's not truly continuous, that has boundaries to it. So for this semester, we're sticking with continuous, but just so you know, there's other possibilities out there. So we started with an empty model, which is just this right here. The empty model has only an intercept, so the intercept then becomes the sample mean. So the intercept is only the sample mean if you have no predictors. And then E is how far off from the sample mean each observation is. So the job of the empty model is to provide a starting point for prediction where everybody's best guess is the mean, and the residual variance in the model, the variance of these e's across people, is all the variance in the outcome there is to be predicted. Then we see how much better we can do by adding predictors. So then we added a slope like this right here, beta 1 times x minus c, where c is my centering constant. And I do that so that x has a meaningful 0 point, because that's where my intercept's going to become. So intercept is the expected outcome when x is 0 now. And beta 1 is my slope that describes how the predicted outcome is going to change per unit change in x. And E is still what's left, how far off my prediction each observation is, and we want to collect the e's. So if x matters, there should be less E variance than before. Whether or not it's significantly less, cough, cough, homework question, is tied to the significance of the slope. The empty model has an intercept and an E. A model with one predictor still has the same intercept and E, but it adds beta 1. So if the E variance is less than it was before adding beta 1, it has to be because of this new part. So if my slope is significant, if beta 1 is sufficiently unexpected given a null hypothesis of 0, then the variance of the e's should be significantly reduced. There's a 1-to-1 correspondence there. And we can put x in as a quantitative predictor, and talk about how y changes per unit of x, going from 1 to 2 to 3 to 4 to 5, or we can put in x as a binary predictor, and a 1 unit change means moving from the group coded 0 to the group coded 1. So a positive slope for a binary predictor means the 1 group has a higher mean than the 0 group. A negative slope would mean that the 1 group has a lower mean than the 0 group. But the slope tells you how the 1 group differs from the 0 group. Same principle, just different application. Okay. Any of that you want to hear again or ask questions about? So I think where we were last week then is this foreshadowing piece. If you only have one predictor in your model, and that predictor's relationship with the outcome can be captured by only one slope, then functionally what you've done is just recreate Pearson's correlation. So the question is, why would you go to all this trouble if Pearson's correlation tells you the same damn thing? Because there are situations, most of the time in fact, when your question cannot be answered with one slope. So where we're headed next then? What if I have a relationship between a predictor variable and an outcome variable that takes more than one slope to describe? So that happens if you have more than 2 groups for a predictor variable. That also happens for quantitative predictors if you want a nonlinear relationship rather than just linear. And it also happens when you have multiple different conceptual predictor variables that you want to examine at the same time. So in all of those cases, Pearson's correlation is not going to answer the question. And that will especially be the case when we start introducing the idea of moderation at the end of the course, which is the idea that the relationship between a predictor and an outcome depends on the values of the other model predictors. So that's coming later on. But all of these situations form the rest of the course in terms of how would you answer a research question under these scenarios. Pearson's correlation isn't going to do it for you. Ta-da! All right, I'm going to stop recording.